All right, so chapter 11, so the first one we're going to do is 11.5, problem 11.5. All right, so we got a lot of stuff in this one. All right, the condenser of a steam power plant contains N equals 1,000 brass tubes with a thermal conductivity of 110 watts per meter Kelvin, each of inner and outer diameter 25 millimeters and 28 millimeter respectively. Steam condensation on the outer surfaces of the tubes is characterized by a convection coefficient of 10,000 watts per meter squared Kelvin. Part A is if cooling water from a large lake is pumped through the condenser tubes with a mass flow rate of 400 kilograms per second, what is the overall heat transfer coefficient based on the outer surface area of the tube? Properties of the water may be approximated, and they give us the dynamic viscosity, thermal conductivity, and the Prandtl number for the water. Okay. Part B is if, after extended operation, fouling provides a resistance of 10 to the negative fourth meters squared Kelvin per watt at the inner surface, what is the value of the overall convection coefficient or overall heat transfer coefficient? Part C is if water is extracted from the lake at 10 degrees Celsius in 10 kilograms per second of steam at 0.0622 bar are to be condensed, what is the corresponding temperature of the water leaving the condenser? The specific heat of the water is 4,180 joules per kilogram Kelvin. All right, so we got a lot of stuff to write down here. Here we have a condenser. It has brass tubes. Here's 1,000 tubes inside this condenser. The thermal conductivity of the tubes is 110 watts per meters Kelvin. The inner diameter is 25 millimeters. The outer diameter is 28 millimeters. The convection coefficient is 10,000 watts per meter squared Kelvin. And they want us to find a few things. So for part A, it's the overall heat transfer coefficient. Okay, and it needs to be based on the outer area. They give us the mass flow rate of the cooling water, which is the cold side, is 400 kilograms per second. They give us water, a bunch of water properties. So helping us not to have to look in the back of the book, right? So they gave us dynamic viscosity, thermal conductivity, and Prandtl number. What's going on here? Just crashed on me. Sorry about that. We got to wait for Microsoft Notes to load up again. Okay, so we have thermal conductivity of the water, Prandtl number, of 6.6. All right, now part B says, let's now get the overall heat transfer coefficient again, but this time we have with fouling. And then part C is the water leaving the condenser. And the water's the cold side, so it's cold side out that they're looking for. And they give us the cold side's inlet, which is 15 degrees Celsius. They give us the mass flow to steam, which is the hot side, which is 10 kilograms per second. And they say the steam condenses at a pressure equal to 0.0622 bar. And then last, the water has a CP of 4,180 joules per kilogram Kelvin. Okay, so we got to draw our schematic yet. All right, so we have our tube. On the outside of it is some steam that's condensing, okay? On the inside is our cooling water, okay? They gave us the diameters. They gave us that this is brass, right? And they gave us this condensing steam's convection coefficient, which is 10,000 watts per meter squared Kelvin. And you get a very high convection coefficient when you're condensing or evaporating. All right, so we need to make some assumptions. I'm going to start with steady state. And fully developed flow. So part A, if we go up, we're looking for the overall heat transfer coefficient. Where do we think we want to begin for this? Go ahead. Sorry.
Start with the COE.
The COE? Is that what you said?
Yeah.
All right. So our COE. All right. COE on which side? On the cooling water, the steam, or the steam and the cooling water?
This condensing steam, because we only know information about that with A.
So, sorry, what was that? Which information do we know a lot about? This is steam. All right, so if we start, I'm just going to go with it. So if we start with the COE, right? Actually, let's write this in a different color. And if we did the water side, we would have Q is m dot Cp T cooling water out minus cooling water in. Okay? On the steam side, all right, so we have over here mass flow rate, this is cold side, right? If we look at this one, they gave us Cp. We have in, but we don't have cooling water out temperature. They're asking for that in part C. And then mass flow rate we do have. Yeah, so right here. But we don't have Q, right? So now if we look at the steam side, is the steam changing in temperature?
No.
No, it's not changing in temperature, it's condensing, right? Does that mean there's no heat transfer? And if there is, how do we have to look at this COE differently with the steam? Yeah, we have to use enthalpy, right? So it's changing phase, so it has that latent energy now, right? So it's the hot side mass flow rate. And we would basically be assuming it's going from a saturated vapor to a saturated liquid. So we just take HFG, which is Hg minus HF. Okay, so that's sat vapor. That's our sat liquid. I know everyone took thermo and would like to forget it, but it comes back to haunt us, right? All right, so then they gave us, we looked through, I think they gave us, yeah, they gave us the mass flow rate of the hot side, the steam, okay? So we still don't have Q, we don't have HFG. Can we get HFG?
We know the pressure.
So we know the pressure, yeah. So that would be enough to look up HFG. Okay. And in the back of our book, it ends up being 2.414 times 10 to the 6th joules per kilogram. That's table A-6. Okay, so we have enough. Now we have HFG, so that would get us Q, which I don't think I have solved directly, but that would get us outlet temperature, the cold side, which is 29.4 degrees Celsius. All right, so we basically solved here. This is part C, right? I think, yeah. So we ended up solving part C here. All right, so we have COE, this. Now, we still need to get our overall heat transfer coefficient. So where do we go for this now?
The resistance circuit.
Yeah, the thermal resistance circuit. So the key on that, right, is we were given geometry, right? We have diameters, we have materials, we have a convection coefficient that's given to us, right? So we can, and we could possibly solve for another one. So we have information to solve for it. So that's where our kind of our key there. All right, so with the thermal circuit, how many resistors do I have?
Two.
Two,
So they should be the 21.
2, 3, 4,
So it should be
I think 3.
D.
3. Okay. Yeah, so we have convection from the steam, we have conduction through the brass, and then we have convection through the cooling one. Sometimes we're able to neglect that conduction, and in this case, we could compare it and see whether we can neglect it. But anyways, it has information, so we can solve for it and see whether it's negligible if we really wanted to neglect it anyway. So we would have then three resistors, right? So if we go from cold side to the hot, we have convection, right? So this would be the inner, let's just say inner. Then we have our wall resistance, and then we have outer, which is the steam. So, all right. So we can put that together. I'm going to use one of the equations they have in the chapter that helps with a more generalized case. So if we look at 1 over our overall convection coefficient times area, that's the same as the inner surface area and the inner overall convection coefficient, or the outer, right? So as long as that overall convection coefficient is with the same area, it's U times A is always the same. Okay, so this looks like this. So we have, actually I'm going to do it down one. All right, so this is going to end up being equation 11.5. And has more terms, right, than we said, because we had 3 resistances up there. So this is 11.5, which is for unthinned. So we don't have any fins on the cold side. We don't have any fins on the hot side, right, on the steam or the water. And it's for a tubular heat exchanger. Okay, so they're tubed, so they already put in the wall resistance you see here already is using cylinders. Okay. All right, so we have in our thermal circuit, we had convection, the conduction, convection. So that means we have neglected and said there's no fouling, right, in part A. So if we look at this, now let's go through and see what we have, what we don't have. We're looking for this, right? So that means we need to come up with equations for the surface areas. We were given the outside convection coefficient, the outer one, which is the steam, so 10,000 right here. We gave in brass thermal conductivity. We don't have length. We're given the inner and outer diameter of that tube, the brass tube. And then we don't have the inner convection coefficient, right? All right, so let's start with the easy parts. Area. Can we solve for the areas, the inner and outer area? Yeah. Okay. Yeah, it's nice and easy on geometry. The inner is pi, the inner diameter of the brass tube, length, right? Outer diameter of that brass tube in length. All right, so we have equations for the areas. Okay, so what do we do with this length, this L? We have the diameters, we don't have L. Any ideas?
Can we multiply it out?
Yeah, it's in every term. So we have length here, the length is here, there'll be a length here inside that area. So it ends up just canceling, or we can think about it as just a 1, unit length of 1. Okay, so we're good there. So then last in this is our convection coefficient on the inner side. So this is our cooling water side. So how do we get that? Or where do we start?
We'll need to find the Reynolds number and then find the coefficient through that.
Yep. Yeah. So we have internal flow, right? So we need to get our Reynolds number, right? So Reynolds number with the mass flow rate is this equation from chapter 8. Okay, so if we look at this equation, they gave us in the problem, they actually gave us the dynamic viscosity. And we have our inner diameter. What is our mass flow rate? So we're looking for the internal flow water. Do we utilize cooling water's 400 kilograms per second?
Yes.
Kind of, okay. So they have one thing in here that tricks it is we have 1,000 tubes, right? This equation for Reynolds number with this mass flow rate utilized the area of one single tube, right? Because it only has diameter here, it doesn't show number of tubes in there. Okay, so we would have to either go back to the original Reynolds number and, you know, and put in, solve for our own velocity with all the surface areas of the tubes, or in this case, basically put our mass flow rate is the mass flow rate of the cooling water divided by N. So we have 0.4 kilograms per second that we put in there. So then that's the Reynolds number in one tube is going to be the same in all those 1,000 of tubes. Okay. So in this problem, it's kind of a common mistake I would see when they have these many tubes. Is just being careful of what equations are looking at a single tube or a bunch of tubes. All right, so if we do that, now we have enough and we have all our values, and we get a Reynolds number of 21,220, which tells us we are,
Turbulent.
yeah, we're turbulent. Okay, so now we have to get our relationship for turbulent, right? Flow. We have our Nusselt number, and we got diameter. We have the thermal conductivity of the water, so we're still looking for that for the water, so that means we need the Nusselt number. So we look up the appropriate one that we need for turbulent flow, internal flow, and we assumed fully developed. So all right, so we have our equation 8.60. We already solved for Reynolds number. Prandtl number was given, 6.6. So we can combine these two equations and solve for enthalpy or solve for Nusselt number and then use that to solve for enthalpy. So we get (3,400) watts per meter squared Kelvin. And now we go way up here. We have our convection coefficient on the inside, on the cooling water. So now we have every term here. We can plug and solve for our overall heat transfer coefficient on the outer surface area. So if we do that, we get 2,255 watts per meter squared Kelvin. Okay, and we see it's close to the convection coefficient on the inside surface versus much further from the 10,000 on the condensing steam. So really the the limiting factor in the thermal circuit is the convection from the cooling water side. Okay. And not the condensing steam's convection coefficient, because that's a very high one, right? All right, so that's, any questions? That's part A. Part B is the overall convection coefficient now with following. All right, so if we go back up, we're looking right here now, right? So what do we do for that?
We add
Use the
thermal circuit.
Yeah, we go back to our thermal circuit, and if we think of our schematic now with this fouling, right, it's just going to have this kind of this layer here on the inner surface. Okay, so now we have that extra resistance of heat transfer from the cooling water to the steam. All right. So back to our equation from our thermal circuit, which is 11.5, again for unfinned tubular heat exchanger. We have that extra resistance back on the thermal circuit, right? So we just have no fouling on the outside surface. Okay, we just have our additional term here, okay? And they gave us this resistance. So we have everything else. So it's just plugging and chugging everything else that we already solved for part A. So with fouling, we get 1,800 watts per meter squared. Kelvin? Okay, so it went from 2255 to 1,800. So you can see why, big heat exchangers, condensers like that, they'll, maybe clean them out after so long. Okay, because the performance is going down as it's fouling and building up this film and being used that much. And then part C we already solved, right? That was just looking at the COE, okay, that we did above. Any questions on this? All right, so I'm going to actually leave it there. We'll do one example from chapter 11 next class, and then we'll move on to the next chapter. So that means I'll probably push the homework problems off a little bit for chapter 11 because of it. Okay. All right, well then that's it for today. If you have any questions, please let me know.
thank you.
Yep, if not, I'll see you on Monday.
All right. Thank you.
Have a good weekend.
You too.